Hi, welcome to Problem Solving Experts. Well, at this point we have defined a problem statement, we have defined the metrics, we have defined the scope for the project, the scope for investigation, and also we have defined a core team and an extended team. As well, we have identified if we are having some attitude problems, and we have solved the attitude problems if necessary through a strategy, an acceptance strategy. Now, if you have solved the problem just involving two people, that's great. But if we have not solved the problem, then it is a technical issue. So we have to work more on the technical side and convert the practical problem into a statistical problem. In previous videos, we have talked about collecting data. Also, in a video, I have talked about, how to obtain a representative sample and how to confirm that our sample is representative. And as well, I have talked about descriptive statistics. But, well, basically, those videos are in preparation for what we are going to talk right now in this session, which is defining which is our baseline performance, which is our performance before implementing improvements, before starting with the investigation itself. So we will define how big is the problem, and the problem will be defined in terms of sigma. If we are having a sigma of 2 or smaller, we are going to have a very big problem. If we are having a sigma between 2 and 3, we are having a big problem. A sigma between 3 and 4, we are having a medium-sized problem. 4 to 5, a small problem, and more to 5, we have not a problem. The sigma is related to DPMOs, defects per million of opportunities, or PPMs, parts per million. As you can see here, for instance, if we are having 308,000 defects per million, which is 30.8% of defects, our sigma is 2. If we are having 66,000, which is 6.68% of defects, then we are having a sigma of 3. And so on. If we are having 0.62% of defects, we are having a sigma of 4, and so on. Now, the sigma, how do we call sigma? Why do we call sigma? In another video, when I talked about descriptive statistics, well, basically, I have defined the standard deviation, and one way to establish the standard deviation or to indicate the standard deviation for a population is through the Greek letter sigma. So if you are talking about the standard deviation for a sample, we are using an S. And well, when we are talking about a standard deviation for a population, we are using the sigma Greek letter to determine the standard deviation. The sigma is quite much related to how many standard deviations fit between the lower specification limit and upper specification limit. For instance, if we are having a 3 sigma process, that means that inside the specification limit between the target and the upper specification limit, 3 standard deviations can fit. One standard deviation, another standard deviation, and another standard deviation fits there. For a 3 sigma process, also between the target and the lower specifications limit, assuming that the process is centered, 3 standard deviations fit in there. 3 sigmas start there. So we are saying that, we are telling that we are having a 3 sigma process because 3 standard deviations plus minus 3 standard deviations, or plus minus 3 sigma, fit inside the specification limits. Well, basically, for instance, if the size of the standard deviation is smaller, which means that the process is having smaller variability, a smaller deviation of each value against the mean, so the sigma or the standard deviation is smaller, more standard deviations will fit inside this range. And for instance, in this example, if we are having something like this one, so we are having, for instance, here, 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 here. So we are having 6 standard deviations that fit here. 1, 2, 3, 4, 5, 6 standard deviations. And same thing here. Let me say that here we are having 1, 2, 3, 4, 5, 6 standard deviations fit in there, then that means that we are having a Six Sigma process. For the same specification limits, the sigma is related to how many short-term standard deviations fit inside the specification limits. That is close related to the defects, that is close related to the probability of having a defect, because for instance, in a 3 sigma process, the distribution curve, assuming that we are having a normal distribution, will be something like that. And in a 6 sigma process, well, the distribution curve will be maybe something like that. So the probability of having defects in a 3 sigma process will be much bigger. For instance, here and here, these areas are going to be much bigger. Here we are having the PPMs, parts per million lower, parts per million upper. So the probability of having defects for a 3 sigma process is much bigger than the probability of having defects for a 6 sigma process. In a 6 sigma process, for instance, well, we are having something like this, and the probability of having defects is very, very small, very small, PPMs or parts per million, or the probability will be very small. So that's why we want to increase the sigma. How? Decreasing the size of the standard deviation. And as I have said, that is closely related to the probability of having defects. Well, so as I have said, we want to evaluate our baseline performance. And if you are having a quantitative metric for your technical primary metric, we are having a continuous variable metric, and you are having a representative sample, I recommend you to take a look to the video that I talk about representativeness of sampling, of a sample. We have to calculate then our sigma performance or our baseline performance. And as I have said, if you have a quantitative metric, recommendation is that you calculate probabilities of having defect. What is the PPM? Well, parts per million, and the PPMs are the probability of defects. How do we calculate that probability? The calculation of that probability is through the proportion of the area below the distribution curve that is outside the specification limits. So we are having the distribution curve, and the area, the proportion of the area below the curve, the distribution curve, those will be the PPMs. If we are having, let's say, 6.6% of the area outside the specification limits, that means that we are having a 3 sigma process. If we are having, well, 0.0233% of the area outside, that means that we are having a 5 sigma process, and so on. Well, before going through explaining the calculation of these areas, which I won't do in detail during this video, but that's part of the class that we are having, the one-to-one class or the face-to-face class. Well, before talking about the calculations of those areas, I want to talk about specification limits. Here we are having proportion of the area below the distribution curve that is outside the specification limits. So, well, let's talk about the specification limits. How to define the specification limits? Well, there are many ways, but actually I'm going to talk about 4 ways to establish specification limits. The first one is when the specification limits are defined by the customer. That is very frequent to happen in automotive industry. If we are a supplier, tier 1, tier 2 supplier of an assembly company, Ford, Toyota, General Motors, etc., and we are a supplier of them, for instance, Nissan, Volkswagen, etc., usually the customer is given to us as suppliers the specification limits. I want these dimensions plus minus this, I want, etc. So they are telling to us I want this resistance, etc., plus minus this, etc. So they provide the specification limits, and that will be the first option. Of course, we want to comply with the specification limits given by the customer. But if not, then we have to, well, the best way, in fact, and in fact I like it better than given by the customer, is to do a functional analysis. Let me talk a little bit more about functional analysis. Functional analysis. In a functional analysis, basically, we have to collect data for our technical primary metric, which can be a product characteristic or a performance of a process or something, and we have to listen to the customer. We have to observe what is the reaction of the customer or the reaction of the person that we want to satisfy. For instance, we can have a technical primary metric here, and we are having our values, the values that we want to determine what should be the specification limits for that metric. And by the other hand, we are also listening to the voice of the customer. In this example, we are having a value of 2.5, and the reaction of the customer is that that was bad. We are having 1.3, and reaction was good, and 1.7 and was bad, and so on. So once that you have the values, which is attribute, because keep in mind that quality is qualitative. That's why the name is quality and not quantity, because it's qualitative, it's subjective, it depends on the customer. So the customer determines it is good, it is bad, it is tasty, it is tasteless, it's expensive, it's cheap, etc. But all of that is perception, it's just reaction, and it's very subjective. But of course we cannot improve what we can't measure. So that's why we have to move from the qualitative world, or the quality perceptions of the customer, into a quantitative world, metrics and the specification limits. Well, once that we have the voice of the customer, qualitative, and our technical metric, our measurements, and we have, both of them, we have to calculate the probability of good or the probability of bad. For instance, if I state the probability of good is equal to E exponential B0 plus B1, the technical metric, divided by 1 plus E B0 plus B1, the technical metric, for instance. And so on. With that, we are calculating what is the probability of having a defect. With that probability, we can determine, we can obtain a curve, for instance. Let me take a look to this one. We can determine our probability in this example is of good, which the probability can be from 0 to 100 of good, and of course the technical metric, or the values for the technical metric, technical metric. And in this example, let me say that we are going to get something like this, which is a curve, and from that curve we will determine, that maybe the lower specification limit should be somewhere like here. And with that we will determine, because most of the cases, let me say that the probability of good is 95%, or whatever the percentage you want to get, and for that 95% probability of good, you will determine your lower specification limit, and greater is better for this specific example. But of course, it depends. In some cases, the specification is we are having a two-sided specification limits. A lot of salt is very salty. No salt, or very small amount of salt, is tasteless, so it's not tasty. So the amount of salt in food should be two-sided, a lower spec, a higher spec, no more, no less, because it won't be satisfying to the customer. In that case, the concept is very similar. We are going to create an equation for probability of very salty, the probability of no salt or tasteless, and with that one we are going to get, maybe something like this one, which will be a curve, perhaps like this one for this other example, and here you will determine what should be the lower specification limit, and also what should be lower specification limit, and what should be the upper specification limit. When you are having one-sided specification limits, you will be using binary logistics regression. When you want to establish two-sided specification limits, usually we are going to use ordinal logistics regression. Basically that is the best approach and the one that I recommend the most. Now, let me talk about the other method to establish specification limits, which is virtual specs. Usually, doing a functional analysis is time-consuming or can be expensive, and sometimes we don't have that time, or we cannot afford to do studies like those ones. So that's why we would prefer, if not possible, to do a functional analysis, and we are not having specifications provided by the customer. Then the next approach should be virtual specification limits. Let me talk about virtual specification limits right now. Well, the next approach is virtual specification limits. Basically, the concept is, I don't know what the customer wants, but I want to improve. And the concept is that I want to reduce my variability, and well, the general rule of thumb is reduce the variability to half. So, how to establish the specification limits? First, you have to collect your data of your process, your data of your product characteristics, and then you have to observe what is the variability, the natural variation that you are having in your process. If your specification limits is two-sided, you don't want to increase, you don't want to decrease the values, but you want to maintain about the mean, then the approach will be that to establish a two-sided virtual specification limits, you will be using the quartiles. Basically, quartile 1 will be a value somewhere like this one. Here is the quartile 1. That means that 25% of the times you are having values smaller than this value, quartile 1. And also you are having the quartile 3. The quartile 3, which is something like this one, is this one, which means that 25% of the times your values are above that value, and they become your specification limits, your upper specification limit and your lower specification limit. And that's it. That's how you will establish your specification limits. What does that mean? That means that your original performance, your baseline performance, will be 500,000 parts per million. And why am I saying that? 50% of your data will be outside these specification limits. 25% of the data will be above that one. 25% of the value will be below that lower specification limits. So 50% of the data will be outside the specification limits, which is 500,000 parts per million. And that means that your baseline performance is going to be 1.5 sigma. Because smaller than 2, that means that your current performance is very bad. Smaller than 2, very bad performance. But that's because we want to improve. That's because if we state that we are good, we won't improve anymore. But if we state right now we are very bad, then we have to do something in this example to reduce the variability and be consistently inside the specification limits. Now, what about if you are having one-sided specification limits? I mean, greater is better. More is better. For instance, yield. You want to increase the yield. Or on-time delivery. You want to deliver product on time. And maybe currently your on-time delivery is 80% and you want to increase the on-time delivery even more. Well, if that is the case, then there are 3 ways to establish the specification limit. One is very aggressive. One is medium aggressivity, and the other one is mild. We don't want to stress too much. So those will be the 3 approaches. For the first approach, well, basically you are having the same thing. You are having your data, which is having some variability in there. And the aggressive approach is that your lower specification limit is going to be quartile 3, which is this one. This value is quartile 3. And what does that mean? That means that, and by the way, that's going to be your lower specification limit. That means that only 25% of the times you are inside the specification limits. So 75% of the times you will be below the lower specification limits, so your baseline will be 750,000 parts per million. So that's really, really bad, very bad. So that will be, and that's why we say that that approach is very aggressive. A second approach will be something like this one, which is quartile 3 minus the span divided by 2. And what is the meaning of that? Well, the second approach is that you are having your process here, something like this one. You are having your quartile 3, which is here, minus the span divided by 2. So basically, this is going to be your lower specification limit. More or less will be the median. It's not exactly the median, but more or less will be the median. If you are having a normal distribution, it will be the median. But well, what is the meaning of this? This means that 50% of the times, you will be below the lower specification limit, which is a sigma of 1.5 sigma. Still very bad, but not 75%, but 50% outside the specification limits. And that is the medium aggressivity approach. Now, let's talk about the mild approach. For the mild approach, it will be, well, something like this one. You have also your, let me erase this part. For the mild approach, you are having something like this one. You are having your variability of your process. You are having the variability of your process. Your lower specification limit will be quartile 3 plus the mean divided by 2 minus the span divided by 2. And then that will be something like this one. And this will be your lower specification limit. Well, basically that means that your lower specification limit is here, which is about 25% of the times you will be outside the specification limits. And well, 75% of the times you will be inside the specification limits. That is exactly the same concept here for the smaller specification limit. The smaller specification limit, the smaller is better. That means that you want to decrease. For instance, if you have a scrap, you want to reduce scrap. And well, for instance, you are having same thing, quartile 3, 25% of the times you will be inside the specs, 75% of the times you will be outside the specs. This medium approach will be that 50% of the times you will be outside the specs, and the mild approach, 25% of the times you will be outside the specs. Again, there is not any reference to the customer, it's just your own performance, because you have demonstrated that 25% of the times you have had those values. Then the question is, why not more frequently? And what I have to do is to increase the mean, reduce variability, or decrease the mean, reduce variability, depending on the type of specification limits that we are having. Once that you have defined your specification limits, well, you are ready. And by the way, you are having also a representative sample, then you can calculate the proportion of the area below the distribution curve that is outside the specification limits. And that will be, well, the PPMs, and from there you will take a look to a table, for instance, and you will be calculating your sigma value, determining your baseline performance, and well, defining how big is your problem. Well, there is a last approach that I have to talk about, establishing specification limits. Personally, I don't like at all that approach, and I will try to avoid. In fact, I didn't want to talk about it, but I cannot be blind, because that is a very frequent approach by many engineers, which is, to me, that is wrong. And basically that is to establish the specification limits from a functional capability analysis. Functional from a process capability analysis. So not a functional, but a process capability analysis. So basically the concept is that we are having a process, that process is having variability, and that is the natural variation of the process. And the concept is that the natural variation of the process is given by the mean of the process, plus minus 3 standard deviations, plus 3 standard deviations and minus 3 standard deviations, and basically that is the natural variation of the process. Usually those limits are known as upper control limit, and lower control limit. The control limits are not given by the customer, are not defined by the engineers, but they are the natural variation of the process. And basically the approach to establish the specification limits is adding one more standard deviation here, plus one standard deviation, and minus one standard deviations here, and well, basically that's how we will determine the upper specification limit, and the lower specification limit. And basically what we are stating is, this is what I have. I don't care if it's good or bad for the customer. I don't mind. What I can do is what I will do, and I won't improve anymore. So this will be my specification limits, and the only thing that I have to do is to maintain that performance, and that's it. So that basically that's not inviting to improvements. It's not encouraging to reduce variability. It's basically, it is what it is. Let's conform with that, and then let's maintain the specs. And basically that's it, which as I have said is very bad approach. But as much as be possible, I will avoid that approach, and I would prefer to use any of the other ones, which is defined by the customer. From a functional analysis, to me is the best one. I would encourage to everyone to do that one as much as be possible. Or virtual specs, which is not the best, but at least what we are stating is, from what I have, I want to reduce variability to half, and basically that's it. At the beginning of this video, I have talked about evaluating how big is the problem. And in order to calculate the size of the problem, we want to calculate our sigma value. In order to get the sigma value, I want to calculate PPMs. PPMs, parts per million. What are the PPMs? The probability of having defects, or the probability of being outside a specification limit, or not being inside the specification limit. Now, how do we calculate those probabilities? With the proportion of the distribution curves, with the proportion of the areas of the distribution curves that are outside the specification limits. So, as I have said, the distribution curve represents the expected distribution of the population. That can be estimated from the mean and the standard deviation of the data of a sample, and also taking a look to the histogram, we can estimate what is the distribution or the expected distribution of the population. Now, if I want to calculate PPMs, I want to evaluate what is the area outside the specification limits, the area below the distribution curve. Then an important value that we have to establish are the specification limits. In a different video, I'm going to talk about how to establish specification limits. But right now, let me take just the specification limits. So if we are having a lower specification limit here, and we are having an upper specification limit here, well, what we have to do is to calculate these areas that are below, well, above the upper specification limit, and the area below the lower specification limit. The proportion of that area will be will be converted into parts per million. For instance, let me say that this, just an example, let me say that this area is 10% of the area. If that is 10%, that will be 10 in 100, 100 in 1,000, 1,000 in 10,000, 10,000 in 100,000, and 100,000 in million. And those will be parts per million, OPER. So that will be the parts per million, OPER. We can do the same thing for the parts per million lower. So the parts per million lower, let me just guess, let me say that this area is 7%. Then the parts per million lower will be 70,000 parts per million lower, below the lower specification limit. And of course, the total PPM will be the sum of the lower PPM plus the upper PPM. Now, the PPMs will be affected by the spread, by the standard deviation or the variability of the data. Because as you can see in this other example here, we are having another population with the same mean, the same average, but a smaller standard deviation because the spread is smaller, the variability is smaller. Then the area below, the area above the upper specification limit will be much smaller, and the area below the lower specification limit will be much smaller. So these areas will be much smaller because the variability is smaller. By the other hand, if we are having the same mean but a bigger standard deviation, a bigger variability, then the area above the upper specification limit and the area below the lower specification limit in both cases will be much bigger than the total number of parts per million will be even bigger. So that's why our objective is always to reduce variability, is always to reduce the standard deviation because, well, as you can see, the effect on the PPMs is big. But by the other hand, also is not only the standard deviation or the spread is affecting to the PPMs, but also the mean. If we take the same example that we are having here, assuming that we are having here a lower specification limit and we are having here an upper specification limit here, so the area that we are having here, let's say again it's 10% and the area here is 7%, which is a total of 100 parts per million, 70,000 parts per million, and total of 170 parts per million. Well, what will it happen if we are having more or less the same distribution with the same variability, but the mean is shifted? The mean for this first example is here. Here is the mean of the population, and in our case the mean has been shifted to the right. Well, then the PPMs will change a lot because this is going to be the lower specification limit. Then the area below the lower specification limit is going to be very low, very small, but this is the upper specification limit. And of course, the area outside the upper specification limit is much bigger, is more than 50% or more than 500,000 parts per million. So as you can see here, although the standard deviation is about the same, if the mean is shifted, there will be a big impact on the PPMs. So both parameters, the mean and the standard deviation, will be affecting to the probability of having defects or the probability of being outside the specification limit. And of course, we can have a combined effect. If we are having a distribution with very small standard deviation, but with the mean shifted from the target, again, in this example, we are not going to have basically almost any PPMs above the upper specification limit, but below the lower specification limit, we can have also a lot of defects, not because of the standard deviation. The standard deviation is much smaller, the variability is much smaller, but because the mean is shifted to the lower side, and then that's why we are going to have a lot of defects. Now, in order to calculate the parts per million, we have to identify what type of distribution curve we are having. There are many types of distribution curves. The most frequent distribution curve is the normal distribution. That is the most frequent that happens in nature, the most frequent that happens in processes, which is basically something like this one, what we have seen. The mean, the median, and the mode are at the center, and well, basically is a bell shape. That is another characteristic. It is asymptotic. And what means asymptotic? Never, this value never touches the axis of 0. This one, this tail, never touches the axis of 0. It's getting closer and closer and closer and closer, but goes to the minus infinite and goes to the plus infinite. So it's asymptotic. By the way, there's another characteristic here, which is the accurate definition of the standard deviation. The accurate definition of the standard deviation. Well, the mean of the population is here. The distance between the mean and the inflection point of the normal distribution, this value is equal to the standard deviation. And that is the accurate definition of the standard deviation. The distance from the mean to the inflection point of the normal distribution. What is the inflection point? Well, the normal distribution, as you can see, is something like this and then like that. So the direction of the curve changes. The point where the direction of the curve changes, that is known as the inflection point. Well, here we are having this direction, and then we are having this direction. This point where the direction changes is the inflection point. The distance between the mean and the inflection point, that will be equal to the standard deviation. For the data that we had, the standard deviation was 1.15. Well, the distribution also is affecting to the PPMs, because as I have said, the definition of PPMs is the probability of having defects, and the probability are the areas below the distribution curve outside the specification limits. The question is, what distribution curve? Does that mean the normal distribution? Well, if the data fit to a normal distribution, yes, of the normal distribution. But if the data do not fit to a normal distribution, then we have to calculate the area of this other type of distribution that is outside the specification limit. For instance, let's say that here I am having a lower specification limit, and we are having an upper specification limit. But the distribution is, so typically the areas would be this area and this area for a normal distribution. But if we are not having a normal distribution like this one, we are having a skew, a tail to the right, then, well, this will be the lower specification limit, and this would be the upper specification limit. And then the areas that we have to calculate are this area and these areas. And those are areas not for the normal distribution, but the areas for a Weibull distribution or whatever that distribution is. Same thing, if the distribution is something like this one, for instance, the area above the upper specification limit, basically 0, but the area below the lower specification limit, it will be something like this one, and then that will be the PPMs, and that's how we have to calculate the parts per million. And that's it. Well, as a problem-solving experts, what we have seen at this point is this. First, we have defined our problem statement. What is the problem to solve? We have defined our metrics. How are we going to measure our problem? We have defined the scope of the investigation. Where are we going to focus the investigation? Where the problem happens more frequently, when happens more frequently, to whom happens more frequently. And now we have established our project team. Also, we have solved all the human behaviors related problems. If with that we have solved the problem, we implement controls to maintain improved state. If not, well, it's time to evaluate our baseline performance. So you have to collect a representative sample. Also, we have already talked about what is a representative sample, how to collect a representative sample, and how to validate if your data are representative. Once that you have evaluated your representativeness of your data, then you have to establish your baseline performance. And the question that we want to answer is, how big is the problem? If we are having a sigma greater than 5, we are not having a problem. If between 4 and 5, we are having a small problem. 3 to 4, medium-sized problem. 2 to 3, big problem. Smaller than 2 sigma, very big problem. To calculate the sigma value, we have to calculate DPMO or PPMs. If you have attribute type of data, we will be calculating DPMO. If you are not having a representative sample, we are calculating DPMO. And you cannot collect more data, of course. But if you are having a good representative sample, then we are having, quantitative type of data, we will be calculating PPMs. PPMs, the probability of having defects. How do we calculate those probabilities? With the proportion of the areas below the distribution curve that are outside the specification limits. What distribution curve should we use? Well, it depends. If it's a normal distribution, we have to use the areas outside the normal distribution. If we are not having a normal distribution, well, we have to deal with non-normal distributions and calculate the areas for the non-normal distributions. Before of that, we can try to normalize the data. In a different video, I will be talking about how to deal with non-normal data. And well, keep in mind that a distribution represents the expected distribution of the population. The histogram of frequencies, that represents the observed distribution of the data, of the sample that you have collected. So from the observed data, you will be making inferences about the population, and from there you will be calculating probabilities. Some key parameters of the data that we have to take in consideration when calculating the probabilities. Well, where is the center? Because the center of the data is affecting to the PPMs. Parameters to measure the center, we can use the mean, the median, or the mode. In most of the cases, because we don't want to take outliers as part of the data, we will be using the mean. And also we have to take in consideration the spread or the variability of the data, because we observe that the PPMs are affected by the variability or the spread of the data. The variability parameters to measure the spread, we have talked about the range, the span, which is the difference between quartile 3 and quartile 1, and the standard deviation. One definition of the standard deviation is the average variation of each value against the mean, and the other one, which is more accurate, is the distance from the mean to the inflection point of the normal distribution or Gauss distribution. Well, we have established our baseline. Now it's time to establish our objectives. Next video, let's talk about how to establish performance objectives.